Hello everyone, my name is Anouk Ehreiser. I'm a master's student of physics at the University of Heidelberg, and I'm also an intern with the European Space Agency this summer through the LEAPS program, which is a cooperation between the University of Leiden and the European Space Agency. I'm going to talk about my research project. We start out with my internship, that is also going to be the project of my master's thesis. So my project concerns looking at Martian analog environments, so environments on Earth that resemble things that we find on Mars, and to extract samples there, analyze them through Raman spectroscopy, close-up imaging, and then have a reference base for the ExoMars 2022 mission that will land a rover on Mars in 2023, and so it can have a reference what to look for when it looks for signs of life on Mars. Here you can see a world map of the distribution of samples. But I want to talk in particular today about one specific area that is like Mount Etna in Sicily. I went there recently for a field trip, and I want to talk specifically about this Martian environment and what we might learn about this and what might be interesting to learn from there about the astrobiology of Mars. So the ExoMars 2022 mission, that's the one where I'm gathering the samples for. It's a mission that already sent an orbiter to Mars. It was launched in 2016, and in 2022 it will launch also a rover and a lander. And on the side you can see the rover, and of particular interest to me is this little gray box that you see there, because this contains a drill system. And the ExoMars rover will basically, people call it an astrobiological laboratory on wheels, and will be the first rover able to drill into the subsurface up to a depth of 2 meters, and will then analyze the samples from there. The landing area is Oxyaplanum. It's of particular interest because it looks like a hydrated clay-rich basin, so it might be a good chance to find organic signs or signs of former life on Mars. You're probably familiar with the early geological history of Earth and Mars, and that actually Earth and Mars very early in the development were quite similar. So, for example, if you look, or if you go back for 4 billion years, that is actually the time when Oxyaplanum was formed, and actually the time also where it might be most likely to find signs of former life on Mars. Why? Because there might have been the possibility that during this time there was actually liquid water on the surface. So indeed you see an artist's impression what this might have looked like. So you see the northern hemisphere is basically covered by an ocean. However, there is dispute over this, if there was ever the conditions of the atmosphere were well enough, if there was ever enough pressure to actually sustain liquid water. So take this with a grain of caution. The interesting thing is about the formation of these salts is, so this is an idea of how the environment could look like. You have geothermal vents, so you actually have volcanic activity, and volcanic activity was very widespread on both early Earth and Mars, and might have provided very important and very distinct environments where life might have lived. So therefore it's interesting for us to understand volcanic environment nowadays on Earth that might resemble them. This is the ExoMars Rosalind Franklin rover, and as you can see there is you can now look inside this little gray box, and inside the little gray box there are 2 instruments, there are many instruments, but the 2 instruments of particular interest to me are the close-up imager and the Raman laser spectrometer, because I have analog instruments that can actually match the capabilities of these instruments. This allows me to go to Martian analog environments, take samples there, and then have a base of comparison with when ExoMars goes on Mars. So the close-up imager is basically a camera system that can take up close-up images, as the name says, of outcrops on Mars. And the process actually is you have the mast, the mast cam, the pan cam. It looks for an interesting outcrop. And then the rover moves there, takes a picture with a close-up imager from different distances. You can also have the Z stacking, so you can basically have you can focus in different layers. And then the drills, and then they can decide where they want to drill, where it looks morphologically interesting for them to drill. You can also see the drill can be tilted, so you can not only drill into the subsurface, but you can also drill into an outcrop. And then once they have a drill core, they can actually use the RLS, the Raman spectrometer, to make a Raman analysis of it. The good thing about a Raman is it can also, even if you have small traces of organic material, Raman can tell you that it is there. However, even if we have interesting results from ExoMars, we also need a certain context in which to interpret this. So this is very important for us to go to Martian analog environments, to look for environments that might resemble conditions on Mars or on past Mars, And for this, I want to talk about a particular Mars analog environment where I collect my samples from, that is Mount Etna. So I went to Mount Etna in July as part of the Euromoon Mars Network Etna campaign. We were a team of several scientists, several engineers. We were all students. It was like a student campaign. So the engineers were very excited about the terrain because, as you can see, it like very much resembles those outcrops and like the gravel that you find on Mars. So the outcrops are actually lava flows, and the gravel is basically ash that falls when you have an eruption. And you can also see from the little picture of an eruption, we actually witnessed an eruption that was very close by. We were only 5 kilometers away, because Mount Etna is also one of the most active volcanoes in the world. It's very well monitored, so there's little danger, but it was still very impressive to see. I don't only want to talk about the lava flows. I also want to talk about another interesting volcanic environment, and those are the salinella. So the salinella are an area of hydrothermal activity that is little to the southwest of Etna, in a town called Paterno. And they're very interesting because they resemble an environment on Mars that are also called mud volcanoes. But I will talk about this later. So first of all, what makes a volcanic environment interesting for astrobiologists? Of course, you want to know how life can adapt and survive in these environments. As you can see, there are very few plants in this area, because actually it is very difficult for plants to grow there, because there are no organic materials in the soil. So most plants, you have some pioneer plants that can survive in these conditions, but usually for most other plants, the volcanic rock has to be broken down first into andosol. And here you can see the ones that produce andosol. So those are lichen. Lichen colonize lava rocks. They're one of the first that can actually colonize them. And as you know, lichen grow very, very slowly, so you need a lot of patience. But this is like an old lava flow from the 18th century, and you can always see like almost the entire rock is covered with different types of lichen. There are also some lichen specialists that specialized on this basaltic lava. And they actually change the surface of the rock. So they enrich it with, for example, aluminium and iron, and they can actually chemically alter the surface and also enrich it with organics. So if like over the centuries this soil breaks down, we produce andosol, and andosol is like a very rich, very good fertilizer. And this is also the reason why you have like on the slopes of volcanoes so much agriculture, because this is like a very rich soil, but only after it's been broken down. From an astrobiological perspective, this is interesting because it gives you a chemical signature that this rock was altered by life. So if we analyze this rock, this might actually give us interesting clues if we later find like fossilized versions of this. So we might not find the life form that did this, but we still might find a clue about erosion that happened due to the weathering of rocks by life. So the other interesting area that I want to talk about are the salinella, so like these very salty mud volcanoes. So mud volcanoes are also suspected to be on Mars, particularly in the northern hemisphere, where there might have been once this large ocean. So on the left side, you see an image of orbit. From orbit, you can see from the scale, it's actually like much smaller. It looks like your usual volcano, but like it's much, much smaller. So it only has a diameter of a kilometer or several hundreds of meters. And on the right side, you can see the same phenomenon on Earth. There are some mud volcanoes from Azerbaijan. Azerbaijan has the highest amount of mud volcanoes in the world, like half of all mud volcanoes in the world are in Azerbaijan. And you can also see some in Canada. So you see there's a lot of similarity between these structures. So like you can understand why people assume that these might be mud volcanoes. There's another clue that those might be mud related, because we find these type of mud cracks. And they're also very similar to the ones that I observed in the mud volcano area in Etna. So you can see like there's my pen for scale, and this large slab of rock was 1.2 meters across. So it's kind of like a very similar scale. How do mud volcanoes form? So they are not formed by lava, but instead you need underground liquid water and gases. And the pressure of these gases actually kind of like leads to a small eruption. And the gases are usually methane and CO2. But usually they are related to volcanic activity, like in the case of mud volcanoes in Etna. The interesting thing about this for astrobiologists is, of course, that if you have a subterranean biosphere where you have liquid water, but it's harder for you to access this from the surface, a mud volcano might give you a direct access to this subterranean subsurface. If you look at these bubbling pools at the salinella in Paterno, you see a large variety of different types. So you see some that are very, very clear water, others are like mixed with clays and are very muddy. You also see a large kind of like differences in shape. in size. Some are around 10 centimeters, larger ones are over 1 meter. And you can also see what they look like when they're dried out, which is, of course, very interesting for people who want to study mud volcanoes, because the ones that you will most likely find are the ones that are dried out. They're called salinella, so they are quite salty. It's mostly sodium chloride. You can also see like some of these crystals on the surface, and they build a very nice layer. So actually having these could having these interesting morphological structures could also be like a good sign of mud volcanism having taken place. And in this area, there are also extremophiles. So there are some bacteria that are particularly adapted to these conditions. They're usually alkalophiles. You don't find thermophiles because actually mud volcanoes are not hot. They are like usually between 10 to 20 degrees. Only sometimes salinella can be hotter, up to 50 degrees, when Etna is particularly active. So to summarize, if we want to understand the results that we get from rover instruments, we have to understand, and we need a basis of reference for similar environments on Earth. Volcanic environments were both widespread on early Earth and Mars. Understanding the chemical alteration of rock by life might be an interesting biosignature that could be further investigated to find if this could be useful. Lava rock, basaltic rock, is also a very good protection from cosmic rays, which also makes, for example, lava tubes or lava caves interesting as a shelter or as a microhabitat. And mud volcanoes are widespread on Mars. However, we have to be careful because the actual physics of mud on Mars might be different from Earth. So like the structure that looks morphologically similar may be actually caused by different processes, and things that actually look different might be caused by similar processes. And of course, mud volcanism is also interesting for astrobiology because it provides a very particular type of habitat where you have an availability of liquid water and where you actually could get an access to the subsurface. Thank you very much for listening to my talk, and I'm available for questions in the live stream.